So let's say that Chase and Sarah live beside each other in the same neighborhood. Same neighborhood with identical driveways. And let's say that Chase and Sarah on Thursday morning get up and there's 80 centimeters of snow there. They get up because their parents got them up. Surprise, there's a snow day today. They're all happy until their parents say, you got to shovel the driveway. Sarah goes out to shovel the driveway. Takes her an hour and a half. It's a lot of snow in that driveway, considering that there's 80 centimeters of snow in that entire driveway. An hour and a half to shovel that driveway. Chase, on the other hand, takes him 4 hours to shovel that driveway. Who's done more work, Chase or Sarah? Sarah's done more work? Why has she done more work? Because she did it faster. Is that right? No, it's not right. Who said they've done the same? Good. They've done the same amount of work. Yes, they've done the same amount of work because in the end, the amount of energy that's required to shovel Sarah's driveway is the exact same amount of energy that's required to shovel Chase's driveway. Sarah did it quicker, but she still expended the exact same amount of energy that Chase did. And since work is defined as the change in energy, that means they've done the same amount of work. Does that make sense? Let's look at an F times D kind of perspective for a second. Now, obviously, they're not going to be applying the same forces over the same displacement each and every shovel load, but on average, they will. On average, their forces that they apply will be the same as each other. And on average, the displacement will also be the same. So, when all is said and done, they will have both done the same amount of work. Now, if you want to hire somebody to shovel your driveway, and you're going to pay them by the hour, then you're probably going to hire Sarah because she's quicker. Now, if you're going to pay them by the job, if you're going to pay them by the amount of work that they do, it doesn't matter who you hire, because they both can do the work. Sarah happens to be quite a bit quicker than Chase, maybe because she's quite a bit stronger than Chase, I'm not sure. But in the end, they can both do the same amount of work. So if you're going to pay them $20 to shovel the driveway or whatever to shovel the driveway, then it's fine. Pay them $20. But if you're going to pay them by the hour, you're going to hire Sarah because she does it quicker. Now, the way we quantify the quickness at which work is done, the rate at which work is done, is to express it in a variable that we call power. Power we define as the rate at which work is done, how quickly work is done. Now, anything that is a rate, anything that's a rate, has time on the bottom. Always. Something divided by time. Remember, velocity was the rate of change of position. So it was change in position over change in time. Acceleration was the change in velocity over time because it was defined as the rate of change of velocity. Well, if we're going to talk about power, which is a rate and is going to have time on the bottom, the rate at which work is done, it's going to be W over T. That make sense? We could also express that, by the way, as delta E over T. Is that okay? Is that reasonable to do? Why is that reasonable to do? Go ahead, Chase. Good, because delta E is equal to W. So sometimes it's more convenient to think of it as W over T. Sometimes it's more convenient to think of it as delta E over T. Now, every once in a while, we may not be given either one, W or delta E. Every once in a while, maybe we're given a force and a displacement, and we've got to do the whole work thing that we learned about last week in order to plug in to the power equation. All right, is power a vector or a scalar? It's a scalar. There's no direction associated with power. What are the units associated with power? Let's look at the work and the time here. Tell me what the units associated with power are. Good, joules per second. Joules per second because we've got work in joules over time in seconds. There's another set of units that we can use for power, though. One that you've heard before, but that we haven't used in Physics 20 yet. What are the other set of units that we use for power? What is the other set of units that we use for power? I'm giving you a hint right now. What is the other set of units that we use for power? It's watt. Watt is the other set of units that we use for power. Chase just said a megawatt. A megawatt is a million watts, right? So if you have a whatever megawatt power plant, then it generates this much electrical power, this many million watts of electrical power, this many million joules per second of electrical power. Make sense? It's a lot of watts. Let's take a look at this question here, 6.11, page 325. It says an elevator and its occupants have a mass of 1,300 kilograms. The elevator motor lifts the elevator to the 12th floor, a distance of 40 meters in 75 seconds. What's the power output of the elevator? And we're not too worried about question B, the efficiency of the system. Okay, what's the power output of the elevator? Clearly, it's a power question, right? And whenever we have a power question, we basically also have a work question. Okay, it may be a work question where we actually have to calculate work using F times D, or it may be a work question just in the sense that we plug the value of work into the equation for power. But we know that both power and work are absolutely valid when we're solving this problem. Let's write down some givens here. We have a mass of 1,300 kilograms. It's this 40 meters thing. It's a displacement. It's moving up 40 meters. And we have a time here of 75.0 seconds. We want to find the power here. Let's say power is equal to W over T. Or we could say that power is equal to delta E over T if it's more convenient for us. We have a time of 75 seconds. All right, good. Well, what else do we do then? We don't have W, do we? W is also equal to what? It's equal to the change in energy, so it's equal to F times D. Do we know what F is? No. Sorry? Good, very good. Work is a change in energy as well. Okay, we can, in fact, it might be more practical in this question to write down power is equal to delta E over T. It doesn't really matter, because it's the same thing. But it may make a little bit more sense to us in this case to write down delta E over delta T. Now, Chase just said the change in energy is equal to the change in potential energy. We're going from the ground level up to a height of 40 meters in the air. What's the final energy? What kind of energy do we have at the end of this? Gravitational potential. So the final energy would be mgh final. What kind of energy does the elevator have before it starts? Nothing. Zero. Now, is there kinetic energy in between? Sure there is. But the initial kinetic energy is zero. And after you get to the top here, 40 meters in the air, and the elevator comes to a stop, the final kinetic energy is zero as well. So the change in energy, the overall change in energy is just the potential, the final potential minus zero over delta T. We got 1,300 kilograms times G, which is 9.81 meters per second squared, times the final height, which is 40.0 meters. Even though we didn't actually have that written down as a height, we had it written down as a displacement, divided by the time of 75.0 seconds. What do we get for that? 6,801.6, and the units to be watts or joules per second. We're going to round that to 3 digits, or 6.80 times 10 to the 3 watts. Good. Chase? Well, here's the thing. Chase's question, I think, if I understand it, Chase, correct me if I am not understanding it correctly, but Chase's question is, could you put in kinetic and potential there? Like basically on your data sheet it says W is equal to delta EK plus delta EP. So could you do this? Is that your question, Chase? Yeah. Yeah, because the zero is because the initial potential energy is zero. Well, no, I put you could skip putting the minus zero because anything minus zero is what it was, right? So you could skip putting the minus zero in there, but you wouldn't have to change the equation in any way to skip the minus zero. The only reason I put the minus zero in there is because the initial energy is zero. The initial kinetic and potential energy is zero. So even if I change the equation to say delta EP over T, it wouldn't change anything. I could skip the zero if I wanted either way. I thought this is what you meant, but let's take a look at this anyways. Could we write that down? Say power is equal to work over time, and on your data sheet it says work is equal to delta EK plus delta EP. Does that work? Sure it does. What's the value of delta EK? 0. Well, then it becomes, Chase, just as you said, delta EP over T, which is MGH final minus MGH initial, which is 0. Make sense? Sometimes you get questions that are quite a bit easier than that. You're just given the value of W and the value of T, solve for it. Sometimes you're given power and T and you have to solve for W or whatever. Sometimes you're given a question that's a little bit tougher. Sometimes you've got to find delta E or W. You can do that by saying F times D, or you can do that by saying final energy minus initial energy. Make sense? All right, what I'd like you to do here, guys, instead of taking a look at the questions that go along with this example, is I'd like you to open up to the worksheet booklet that I gave you here last week and take a look at the second worksheet. Worksheet number, I guess they're not numbered. The second worksheet, which is titled Power. And I'd like you to take a look at those questions for the next few minutes, please, the Power worksheet. See what you can do those, and then we'll go over a couple of them in just a couple minutes. All right, everyone, let's take a look at the question number 6 on your Power worksheet. It says a bicycle is pedaled at a speed of 22 kilometers per hour for 20 minutes. The power output of the cyclist is 400 watts. What's the average force that the cyclist applied on the bicycle? Let's write down some givens here. Clearly, we know that work and power are both relevant to this question. We've got a speed here of 22.0 kilometers per hour, which in the end we're going to convert to meters per second. Our time here is 20.0 minutes, which again we're going to convert here. We don't want minutes, we want seconds. We'll do that in a second here. We've got a power output here of 400 watts, and we want to find the average force here. Let's do the conversions here now. What's 22 kilometers per hour in meters per second, Caden? 6.111. We multiplied by 1,000 and then divided by 3,600. So we get 6.111 meters per second. 20 minutes, we got to multiply that by 60 to get seconds. So it's going to end up being equal to 1,200 seconds. And we've got power in watts already. We want to find the force. Here's what I did. Now, tell me if you did something different and got the correct answer, okay? I said power is equal to W over T. Is that a valid equation here? Yes, it is. W is also equal to what? It's equal to the change in energy, and it's also equal to F times D. So I said W is equal to F times D over T. Now, watch this. This is kind of a tricky thing. It's not the only way to do it, but it's a nice little shortcut if you spot it. What's D over T equal to? Velocity. So power becomes equal to force times velocity. And I've got the power, and I've got the velocity. All I want to do is find the force. Does that make sense? All I've done is replaced delta D over delta T with velocity. And the equation becomes for power F times V. Now, if you didn't spot that, that's okay. Okay, it just means a little bit of extra work if you didn't spot that. Okay, the other way to look at this is say, look, okay, F times D over T. Let's find D. We know what V is and we know what T is. Let's use my equation V equals D over T, or D is equal to V times T. When we multiply V times T, we get 7,333.333 meters. Well, now we can say power is equal to, we can rearrange that, solve for force. We've got power, we've got D, we've got T, and we can rearrange it to solve for force. So you can actually get the value of displacement given the value of velocity and time, and then rearrange it to solve for force. Or if you spot that shortcut, you can just replace delta D over delta T with velocity and not bother going through that calculation of getting delta D. The answer when you do that math works out to be 65.5 newtons. Anybody get that value, 65.5 newtons for force? Okay, good. How'd you do it? Did you do it the shortcut way or the long cut way? The long cut way. And that's fine, right? That's the way, honestly, that I would expect most of you to do it. Okay, in fact, the first time that I did it, that's the way that I did it too. I didn't spot the shortcut right away on that one either. And then it just kind of occurred to me afterwards, hey, wait a second, I could do this. Okay? Doesn't matter. Let's take a look at question number 7 as well, okay? So power worksheet, question number 7. This one says a small engine produces 6,000 joules of energy per second. What are we given there? Produces 6,000 joules of energy per second. That's power. Okay? Joules per second. Power is 6,000 or 6.0 times 10 to the 3 watts, or 6.0 times 10 to the 3 joules per second. We're looking for displacement, how far it's going to push it. We're given the mass of this thing is 3.0 kilograms. And we have an average force of 200 newtons. Once again, we know that work is, or power, I should say, is equal to work over time. We also know that work is equal to F times D. Let's just solve for W here right now. Can we do that? We don't have time, do we? We don't have T. So what are we going to do here? Sorry, work is not equal to, yes it is, yeah. What are we going to do here? What did I do when I solved this? We're going to, let's try this. Let's stick in the F times D over T here. Is that going to be helpful to me? I've got, How can we find displacement? Oh, you know what we can do? Yeah, you know what we can do? We say that the power is equal to 6,000 watts in 1 second, or 6,000 watts, 6,000 joules per second. We could say just as easily, W is equal to 6,000 joules, and the time would be 1.0 seconds. Does that make sense? Does that make sense, guys? Well, listen, think about it. If it's 6,000 joules per second, then we could say the work is 6,000 joules in a time of 1 second. Does that make sense? You know what, we have to assume a time there. This is a poorly phrased question, actually. If we assume that time of 1 second, that's okay. But when we look at the way the question is phrased, it doesn't actually say that. The engine produces this much of energy per second, and that's fine to say that. But then it says, how far will it push a 3-kilogram object if it's able to apply an average force of 200 newtons on the object? Is that for 1 second? Or how long are we applying the force for? It doesn't actually say that, right? We need to know in this question how long we're applying the force for. So if we applied the force for 10 seconds, well, then this question becomes rather straightforward. We've got the power, okay, we've got the force, we've got the time, we solve for the displacement. But we need a time here. And now we can say that work is equal to 6,000 joules, the time is 1 second, and that's true in terms of joules per second, but that doesn't mean necessarily that the force is being applied for 1 second, because it doesn't say that. Okay, so it's a poorly phrased question, and really not a doable question with what we have there. I did it, and I got an answer, but I'm not even going to give you the answer because it doesn't really make any sense because the question was so poorly phrased there. So let's just scratch question number 7. Okay, let's not worry about it. I apologize for giving you that question because in the end, the question's not bad. It's just I should have given you the time for that question. That's all. Last topic of the unit here, everyone. Real quick question. What's mechanical energy? Energy done by a machine? Could be. Could be. Yes. Mechanical energy is simply EK plus EP. The total mechanical energy of an object is its total kinetic energy plus its total potential energy. If you ever want to find the total mechanical energy, then let's calculate its potential, let's calculate its kinetic, and then let's simply add them together. It's not that hard. You just got to know what it is, that's all. Now, what does the word conserve mean? Conservation, conserve. Sorry? Store, not exactly, but you're not completely off base on that. Equal, yeah, you're getting closer. Keep, yes, good. Keep, stay the same. Not change it. The law of conservation of mechanical energy says this. It says, in fact, the same thing as the first law of thermodynamics that you learned in Science 10. It says the total mechanical energy, that's the total kinetic and potential energy of an object, will always remain the same. If we account for everything, okay, if we account for everything, the total mechanical energy will always remain the same. In other words, you got a roller coaster going down a hill, and you're going to experience this next Tuesday, okay, 8 days from now. Okay, the roller coaster goes down the hill. You've got a certain amount of potential energy at the top of the hill, and maybe a little bit of kinetic energy at the top of the hill because it's moving as well, but mostly potential. At the bottom of the hill, you've got no potential, and you've got a heck of a lot more kinetic energy at the bottom of the hill. But if you compare the total mechanical energy at the top of the hill to the total mechanical energy at the bottom of the hill, it's going to be the same. Total mechanical energy remains constant if we account for everything. Okay, another way we can say it, well, if the total mechanical energy is going to remain the same, then energy can't be created or destroyed. It's going to transform from one type to another. At the top of the roller coaster, we've got potential energy. At the bottom of the roller coaster, we've got kinetic energy. It's transformed from potential to kinetic, but the total amount remains the same. Nothing was created and nothing was destroyed. Now, sometimes it appears as if energy is not conserved. Sometimes it appears as if energy is either created or destroyed, but it isn't. If it appears as if energy is created, you get more energy in the end of the problem that you had in the beginning of the problem. Well, it's probably because you gained energy because of wind or something. It doesn't mean it was created. It just means that you didn't account for everything. Okay, if you account for everything, including the wind, then the total amount of energy is going to remain the same. Maybe if energy is lost due to friction. Well, again, it appears as if energy is destroyed in that case because maybe it's slower at the end than it is at the beginning. Friction's taking energy away. But it's not destroyed. If you account for all the energy, including the energy that was taken away due to friction, the work done by friction, then again, you're going to find that the total mechanical energy is going to remain the same. Tanner? What about wind turbines? In the end, energy will still be conserved. Sometimes it's going to appear as if you lose energy due to friction and all that kind of stuff. But in the end, total energy is still going to remain the same. You can't create or destroy energy. You've got kinetic energy in the wind, and that's ultimately going to be transferred to kinetic energy in the turbine, which is ultimately going to be transferred to the electrical energy that's transmitted. I'm sorry? The wind surpasses the electrical energy, or the electrical energy surpasses the wind? No, it doesn't. No, it doesn't. You can't get more electrical energy out of a system than you had kinetic energy in the wind to begin with. It's impossible. Doesn't matter what gear system you have. And I don't know the inner workings of it, Tanner, like what kind of gearing system is inside a turbine, but in the end, you can't get more electrical energy out of the system than you had kinetic energy going into it. It's impossible. It's possible. Yes, that's perfect question. It means you have more than 100% efficiency, which isn't possible. Okay, it violates fundamental law of physics, first law of thermodynamics, the law of conservation of energy, which is probably the single biggest physics law that we have. Not just physics 20, not just physics 30, but period. The single biggest physics law that we have, the law of conservation of energy. So sometimes we gain it because of wind. Well, we're not really creating it. It's just added to the system. If we account for everything, then total energy remains the same. Sometimes you lose it because of friction or air resistance or something like that, but it's not destroyed. It just looks like it is. If we account for everything, including the energy lost due to friction or air resistance or whatever, then we're going to find that the total energy remains the same. Now, the problems that we're going to solve are problems in which air resistance, friction, wind, anything that adds or takes away energy to or from the system is going to be so small that we're going to neglect it. It's negligible. It means it's a really, really small number. If that's the case, if we're able to neglect air resistance and wind and friction and all that stuff because it's so small, then we can mathematically state the law of conservation of energy in this way. EI is equal to EF. The initial energy, the energy that we start with, is equal to EF, the energy that we finish with. Different kinds. You might have kinetic at the beginning and potential at the end, or vice versa, but the total initial energy will be equal to the total final energy. Got an example for you here. It says a 500-gram ball is thrown downward at a speed of 5 meters per second from a height of 35 meters. What's the speed of the ball as it hits the ground? We could solve this problem using our old kinematic stuff. D is equal to VIT plus 1/2 AT squared, or VF squared is equal to VI squared plus 2AD, or something like that. But again, I'm just giving you now something else. Just like with that whole W is equal to delta E that we had last week, we could solve with that old kinematics and dynamic stuff. Okay, I gave you a method that was a little bit quicker and more efficient. Okay, same thing here. We're giving you a more versatile method now, this whole idea of the law of conservation of energy. Copy this question down, and then we'll do the question using conservation of energy, even though we could do it using some of the old physics that we learned way back at the middle of September. So the ball is thrown downward at a speed of 5 meters per second at a height of 35 meters. The speed of the ball is what we want to find. Understand the versatility of this whole conservation of energy method, this whole law of conservation of energy, allows us to solve problems whether it's thrown straight down or whether it's a 500-gram toy at the top of a hill, going to the bottom of that. It doesn't matter. It doesn't matter what path it takes. Energy is a scalar. That's the beauty of it. Energy is a scalar. So it doesn't matter whether it goes straight down or whether it goes down a hill at an angle, like an inclined plane, one of those hill problems, or a roller coaster problem, or anything. It doesn't matter. The direction doesn't matter. What matters is where it starts and where it ends. Okay? We're going to say, because this is a problem in which there's a change in height, in which there is an energy conversion taking place here, we're going to say EI is equal to EF. That means that the initial energy is equal to the final energy. If we're ignoring friction and air resistance and wind and all that stuff, which we'll assume that there is very little of that, then the total initial energy will be equal to the total final energy. Now, here's the crux of this method. You got to ask yourself at the beginning of the problem and at the end of the problem the same two questions. Question number one, is there a height? At the beginning of the problem, is there a height? If there's a height, there's potential energy. There's MGH. At the beginning of the problem, is it moving? Yes. So we're going to add to that kinetic energy. Don't multiply it. Remember what we said. Mechanical energy is the total of potential and kinetic. Add them together. The total initial mechanical energy is potential plus kinetic. Now, at the end of the problem, is there a height? No. At the end of the problem, it's on the ground. So we don't have potential at the end of the problem. But at the end of the problem, is it moving? Yes. So we're going to say that there is kinetic energy at the end of the problem. My equation becomes mgh initial plus 1/2 mvi squared plus 1 equals 1/2 mvf squared. Now, there's a bit of a shortcut here. You don't have to spot it, but if you do, it saves you a little bit of work. What is it? You can cancel out the masses. Why? Good. It's the same mass in every term. You can cancel out that mass. Okay, look at each individual question. If the mass appears in every term, then you can cancel out the mass. Sometimes you may be given a question without the mass, not even given the value of the mass. Okay, it doesn't matter. Cancel it out. And think about that. If you drop an object or you throw an object, we know that all objects accelerate downward at the same rate, 9.81 meters per second squared. The mass doesn't matter. So why wouldn't the mass cancel out? Why would the mass matter here? Let's plug in some numbers. Remember, energy is a scalar, so everything's going to be positive here. 9.81 meters per second squared. The initial height is 35.0 meters. We add to that 1/2 of VI squared, 5.00. Don't forget to square that. Equals 1/2 of VF squared. Let's get the left-hand side there. 9.81 times 35. Say 9.81 times 35 gives us 343.35. We add to that 1/2 of 5 squared, which is going to be 12.5, equals 1/2 of VF squared. Let's add 343 now plus 12.5. Gives me 355.85 equals 1/2 of VF squared. How do I take the half over? Two ways. Okay. I can multiply by 2, or I can divide by 1/2. It's going to give me the exact same number there. 355.85 times 2 is going to give me 711.7. Is that right? 711.7 equals VF squared. Now how are we going to get rid of the square? We're going to square root it, right? Square root of 711.7 is going to give me somewhere in the range of 26. So 26.67. 26.7 meters per second. Make sense? Michael? Why would you do it this way when you could use VF squared is equal to VI squared plus 280? That's a good question. Okay, that's a perfectly fair question. Why would you do it this way? Because this way it seems to be a little bit longer, right? Well, in the end, it's actually not longer, and I'll show you how it's not really longer in just a second. But in the end, we do it this way, this particular question this way. Sounds silly for a second, but because we can. We'll do it this way because we can. This method becomes versatile for problems that it becomes more difficult to use. Certain things like VF squared is equal to VI squared plus 280. But in the end, all of them are doable using another method. It's just that sometimes this becomes the best method to do. And we're starting off with a nice simple question, a nice straightforward question, where it'd be quite easy to solve it in another way. But it allows us to get some practice using this method. Michael said, why don't we just use VF squared is equal to VI squared plus 280? Okay, like I said, that's a perfectly valid thing to ask. It's a good question to ask. Well, Michael, take a look at what we've done right here. What do we have right there after we've canceled the masses? We've got G times HI plus 1/2 of VI squared equals 1/2 of VF squared. Okay, it looks completely different, right? Let's rearrange this, okay? Let's rearrange this. Let's take the 2 over by multiplying. I get 2 times GHI plus, well, 2 times 1/2 is 1. So it becomes VI squared equals VF squared. So if we just change the order of that, VF squared becomes equal to VI squared plus 2GH. What's G? What's H? So it's the same thing, really, right? It ends up being the same thing. In fact, this equation comes from the law of conservation of energy. We just didn't tell you that back in the middle of September. Tanner? How to get rid of the half right there? I multiplied everything on the left side by 2, so it became 2 times this. And then when I distributed the 2, it became 2GH plus 2 times 1/2, which is 1. Okay, you don't need to be able to do that. I'm just kind of making a little extension from Michael's question there. So it's really the same thing, Michael. It's probably a little bit quicker maybe to use that, but not much, or that I should say, but probably not much. No, on the test I won't tell you what to use. In the end, I'll mark anything correct that you've done correctly on a test. Okay? Even if you've used a method that I'm not expecting, I'll mark it correct. Hold on for 1 second here, guys. Let's take a look, please, at your conservation of energy worksheet. Let's do for homework, please, the first 3 questions. The first 3 questions on your conservation of energy worksheet. Do those for tomorrow. We'll check those over. We'll see how they go, and that's pretty much it for our unit. Have a good night, everyone.